Hello everyone, myself Dr. Harisankar Singh. So far, we have learned about the various laws that were foundation of Maxwell equation in the static field. Now, in this video, I will discuss the equations of electromagnetism, that is Maxwell equations. This video will be focused on the Maxwell's first equation and rest three equations we will cover in the upcoming videos. So let's start. Here I am starting with little bit from history where it came into the limelight. Basically, the Scottish physicist James Clerk Maxwell is regarded as founder of electromagnetic theory in its present form. Maxwell published the first unified theory of electricity and magnetism. The theory comprised that all previously known results, that is basically Gauss law of electrostatics, Gauss law of magnetostatics, Faraday's law and Ampere's law, both experimental and theoretical. It further introduced displacement current and predicted that the existence of electromagnetic waves. And this was given by Maxwell. Maxwell's equations were not fully accepted by many scientists over the world till 1888, where they were confirmed by the Henry Hertz, who was a German physicist, and he generated and detected radio wave successfully. After that, Maxwell equation was accepted over worldwide. The law of electromagnetism, that is Maxwell, put together in the form of four generalized equations, and this equation is given for the time varying condition and are given in the table. You can see here this table is having both differential and integral form of the Maxwell's equation. The integral form of the Maxwell's equation shows the underlying physical laws, whereas the differential form is used more frequently in solving the problems. So here you can see the first law of Maxwell equation is Gauss law of electrostatics, where in the differential form it is written as del dot D is equal to rho v, and in the integral form closed surface integral d dot ds is equal to volume integral rho v dv. And in this video we will discuss more about this equation. And the second equation of Maxwell is Gauss law of magnetostatics, which defined as in the differential form del dot b is equal to 0, whereas in the integral form closed surface integral b dot ds is equal to 0. And this shows that never exists isolated magnetic poles. It always exists north pole with south pole or south pole with north pole. And the third law of electromagnetism, that is the Maxwell third equation, says that del cross E is equal to minus del B by del T in the differential form, whereas in the integral form it is written as closed integral E dot dl over contour C is equal to minus del by del T surface integral B dot ds. And this is the equation of Faraday's law. Here Maxwell tells about the due to rate of change of magnetic flux, electric field are induced. And the fourth law of magnetism, that is the Maxwell fourth equation, is given by del cross H is equal to J plus del D by del T. In the integral form, it is written as closed integral H dot dl over contour C is equal to surface integral over surface S J plus del D by del T dot ds. Here two currents are given, that is J plus del D by del T. The prediction of Maxwell was displacement current, and it was represented by del D by del T, that is nothing but it is simply displacement current, and prediction was done by Maxwell. Thereafter Ampere's law was modified, and this equation is known as Maxwell's fourth equation. Thus we can say that for a field to qualify as an electromagnetic field, it must satisfy all four Maxwell's equations. In this video our focus will be on the first Maxwell's equation only, that is Gauss law of electrostatics. So Maxwell's first equation is basically the Gauss law of electrostatics. In the integral form, it is written here closed surface integral E dot n cap dA is equal to Q enclosed by epsilon naught, where the left hand side of this equation is no more than a mathematical description of the electric flux. It means the number of electric field lines passing through a closed surface S, whereas the right side is total amount of charge enclosed within that surface and divided by constant called permittivity of the free space, that is epsilon naught. To help you understand the meaning of each symbol in the integral form of the Gauss law of electrostatics, here is the expanded view are given, where you can notice everything which their meaning are mentioned here. So you can see here the integral is used to sum of the contribution from each portion of the surface, and electric field is a basically vector quantity. That is why we have used arrowhead over the electric field, and this dot is basically dot product and tell you to find the part of electric field parallel to the n. N is the basically unit vector and it is normal to the surface, and dA is the incremental surface area in the meter square, and this was equal to Q enclosed by epsilon naught, where Q is the amount of charge in coulombs and ENC is used, that is charge enclosed. That means whatever charge enclosed within that surface, we have to find the electric field, and epsilon naught is the electric permittivity of the free space, and this S indicates that surface integral, not line or volume integral. Now, to understand the Gauss law, you have to know the concept of electric field, as we have already discussed during the electrostatics lectures. It was Michael Faraday who first referred to an electric field of force, and James Clerk Maxwell identified that a space in which electric forces acts. So we can define an electric field in an electrical force per unit charge exerted on a force object, and it can be written as E is equal to F divided by Q naught, where vector F is the electrical force on a small charge Q naught. Here, this given definition shows two characteristics of electric field. First, electric field is a vector quantity with magnitude directly proportional to the force, and also electric field has unit Newton per coulomb, as force have unit Newton and charge have unit coulombs. So we can write electric field have the unit as Newton per coulomb, and which are same as volt per meter. Now, to visualize the electric field in the vicinity of charged object, one can sketch and use either arrows or field lines that points in the direction of field at each point in the space. Look at these charges as shown in the figure. Here are few rules of thumbs that will help you to visualize and sketch the electric fields produced by the charges. The electric field lines must originate on the positive charge and terminate on the negative charge, and the net electric field at any point is the vector sum of all the electric fields present at that point. And also, electric field lines can never cross to each other, since that would indicate that the field points in two directions at the same location. And also, electric field lines are always perpendicular to the surface, and we have already discussed in the previous videos during the discussion of electrostatics. And now you can look at this figure. You can see 2 point charges are here. One is the positive charge, another is the negative charge. For the point charge, electric field lines diverge outwards. That means field lines are always out of the positive charge. And for the negative point charge, electric field lines converge towards the itself. That is, the direction of field line is inward direction. An infinite line of the positive charge, the electric field lines are at a distance r from the line, where r is radius of cylinder. And for the infinite plane of negative charge, the charge is distributed over the surface as surface charge density. And if it is negative charge density, then electric field lines are in inward direction. And for the positively charged conducting sphere, the electric field lines are outward direction at a distance r from the center of sphere, where r is the radius of sphere. And for the electric dipole, which have the positive charge and negative charge both. So you can see in this figure the positive charge on left side and negative charge on right side. You can see the electric field lines originates from the positive charge and ends on the negative charge. Now we will see what is Q enclosed, that is defined as enclosed charge. We have already discussed it in the detailed manner during the electrostatics discussion. As we know, the Gauss law involves only the enclosed charge, that is the charges within the closed surface over which the flux is determined. Any charge located outside the surface produces an equal amount of inward, that is negative flux, and outward, that is positive flux. So the net contribution to the flux through a closed surface must be zero. So for problems involving groups of discrete charges enclosed by the surface of any shape, finding the total charge is simply a matter of adding the individual charges. So total enclosed charges can be calculated as within the closed surface summation I qi, where I is the number of charges within the closed surface. As you can see this figure, you are free to choose a surface that surrounds a known amount of charges. In each of these cases, the total charge within the selected surface can be easily determined from the geometrical condition. That is, for a point charge, we can use sphere for enclosing it. For multiple point charges, we can use cube or cuboid for enclosing it. Whereas for the charged line, we can use cylinder for enclosing it. And over these surfaces, we have to calculate the total amount of charge enclosed within that surface, and due to that, we have to find total electric field line passing through these surfaces. And therefore, we will calculate the electric flux and we have to solve the problems. Now, I will discuss the Gauss law of electrostatics in the differential form. So, in the differential form, we can write as del dot E is equal to rho v by epsilon naught. So, the left side of this equation is a mathematical description of the divergence of electric field, and the right hand side is the electric charge density divided by permittivity of the free space. As you know, the electric field produced by the electric charges diverge from the positive charge and converge upon the negative charge. In other words, you can say the only places at which the divergence of electric field is not zero are those locations at which charge is present. If the positive charge is present, the divergence is positive, meaning that electric field tends to flow away from the location. That means the electric field lines will be in the diverging nature. If negative charge is present, the divergence is negative, meaning that the field lines tends to flow towards that point. That means electric field line towards the inward direction. According to the divergence theorem, we know that it is used to convert the surface integral into the volume integral. So we have already defined The electric field line passes through a closed surface, that is surface integral E dot n dA. Now we want to change this surface integral into the volume integral. So according to the divergence theorem, this surface integral can be converted into the volume integral after integrating over the volume the divergence of the field, and it is equal to volume integral rho v by epsilon naught dv. On equating the volume integral of both sides, we will get del dot E is equal to rho v by epsilon naught. And this is the basically differential form of the Gauss law of electrostatics, or you can say first Maxwell equations. And in terms of electric flux density, it is defined as del dot D is equal to rho v. This is again differential form of Maxwell first equation. Here the full explanation of the differential equations are given. Here del is the basically operator. It is known as del, or you can say nabla, and it is the vector quantity, so arrowhead is present. The dot product turns the del operator into the divergence, and electric field is a vector quantity, so here the arrowhead is present, and electric field have the unit Newton per coulomb or volt per meter, and rho v is the volume charge density, and it is enclosed within the surface, and epsilon naught is the electric permittivity of the free space. Note that there is a fundamental difference between the differential and integral form of the Gauss law. The differential form deals the divergence of electric field and the charge density at the individual points in the space, whereas integral forms gives the integral of normal component of electric fields over a closed surface. The familiarity with both the forms will give you idea to use whichever is better suited for the given problem. And other three equations of the Maxwell will be discussed in the next upcoming videos. Thank you for watching this video.